Have you ever pondered about the vastness of the universe and how we, as humans, fit into this cosmic jigsaw? In the grand scheme of existence, we're but a speck, a fleeting moment in the infinity of time and space. The universe, a vast expanse of darkness speckled with stars, galaxies, and cosmic phenomena, is an enigma. A mystery that has captivated and confounded us for millennia. Our curiosity propels us to explore, to seek answers, to understand. It's the same curiosity that led us to fire, to the wheel, to the splitting of the atom. And it is this curiosity that drives us to comprehend the cosmos, to understand our place within this vast, infinite expanse. We yearn to decipher the cosmic code, to unravel the universal truths that govern our existence. One of the key pieces of this cosmic puzzle lies in understanding Einstein's theory of relativity. At the heart of our cosmic understanding is a man named Albert Einstein. A physicist by profession, Einstein was a curious and innovative thinker who dared to look beyond the accepted norms of his time. His explorations into the realms of the unknown led him to formulate some of the most groundbreaking theories in physics. Born in Germany in the late 19th century, Einstein's interest in science was kindled early, and he spent his life pursuing answers to the universe's most profound questions. His most significant contribution came in the form of his theory of relativity. This theory, composed of the special and general theory of relativity, broke away from Newtonian physics and introduced concepts like spacetime and gravity as a curvature of this spacetime. Why are his theories so crucial? Well, they provide the framework for our understanding of the universe's fundamental laws. Without them, we would be left to navigate the cosmos without a compass. Einstein's theory of relativity fundamentally changed our perception of space and time. So, what exactly is the theory of relativity? Picture a trampoline. Now, imagine placing a bowling ball in the middle. What happens? The weight of the ball distorts the trampoline, creating a depression. This is a simple analogy for understanding the theory of relativity. Here the trampoline symbolizes the fabric of space-time, and the bowling ball represents a mass, say a planet or a star. The depression it causes is akin to the gravitational field it creates. Einstein's theory of relativity consists of two parts: the special relativity and the general relativity. Special relativity, proposed in 1905, tells us that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is the same, no matter the speed or direction of the observer. 5 years later, Einstein introduced general relativity, extending the principle to include gravity. Here's where our trampoline analogy comes in. According to general relativity, massive objects cause a distortion in space-time, which we perceive as gravity. So, a planet moving along this curved path is merely following the curvature of space-time caused by its mass. Now, let's talk about space-time. It's a four-dimensional fabric that combines the three dimensions of space, length, width, and height, with the one dimension of time. Think of it as a grid that stretches out infinitely in all directions. The presence of mass and energy warps this grid, curving space-time around it. So the path that a moving object will follow through space-time is determined by this curvature. If space-time is flat, the object will move in a straight line, but if it's curved by mass or energy, the object will move along a curved path. That's what we see as gravity. In essence, Einstein's theory of relativity tells us that space and time are intertwined into a four-dimensional fabric called space-time, which is warped and curved by mass and energy. To truly grasp the theory of relativity, there are a few key concepts we need to understand. First up, we have the speed of light, often referred to as c in scientific parlance. This universal constant is the cosmic speed limit, clocking in at a staggering 186,000 miles per second. Einstein proposed that this speed is the same for all observers, regardless of their motion or the motion of the source of light. This was a radical departure from the classical physics of Newton, which had no such speed limit. Next, we delve into the fascinating realm of time dilation. Simply put, time dilation is the idea that time isn't consistent or absolute. Instead, it's relative and can stretch or squeeze depending on the speed at which you're moving or the strength of the gravitational field you're in. So, if you're zooming around the cosmos at near light speed or hanging out near a heavy planet or a black hole, your clock will tick slower compared to someone who's stationary relative to you. The third key concept is length contraction. This phenomenon suggests that an object in motion will appear shorter along the direction of motion to a stationary observer. Imagine a spaceship flying past you at near light speed. To you, the observer, the spaceship would appear contracted or squished. But for the passengers inside the spaceship, everything would seem perfectly normal. And lastly, we have the equivalence principle, which states that the effects of gravity and acceleration are indistinguishable from each other. Picture yourself in an elevator in space, accelerating upwards. You'd feel a force pushing you down, just like gravity on Earth. This principle laid the foundation for Einstein's general theory of relativity, which describes gravity not as a force, but as a curvature of space-time caused by mass and energy. These concepts, though challenging to comprehend, are the building blocks of Einstein's revolutionary theory. Einstein's theory of relativity has had a profound impact on our understanding of the universe. And that's no exaggeration. This revolutionary theory has essentially reshaped our perception of reality, offering us insights into phenomena that were once considered the stuff of fantasy. Take black holes, for instance. These mysterious cosmic entities were first predicted by the theory of relativity. It suggested that if a mass is dense enough, it can warp the fabric of space-time to such an extent that nothing, not even light, can escape its gravitational pull. This was a radical idea, but we now have compelling evidence of black holes' existence and their profound impact on the universe's structure. The theory of relativity also opened up the tantalizing possibility of time travel. According to Einstein's equations, time is not a constant but rather a variable that can be affected by speed and gravity. The faster one moves, or the stronger the gravitational field one is in, the slower time passes. This concept, known as time dilation, has been validated by numerous experiments. And although practical time travel remains the stuff of science fiction, the underlying principle is a cornerstone of modern physics. Moreover, the theory of relativity has given us a new understanding of energy and mass. It posited that energy and mass are interchangeable, summed up in the iconic equation E=mc2. This insight has had far-reaching implications, from the development of nuclear power to our understanding of how the sun shines. But perhaps the most profound impact of the theory of relativity is its implications for the nature of the universe itself. It has suggested that the universe is not a static, unchanging entity, but rather a dynamic, evolving system, expanding and evolving over billions of years. Without Einstein's theory of relativity, our understanding of the universe would be fundamentally different. Indeed, this groundbreaking theory has not just expanded our knowledge of the cosmos, but has fundamentally reshaped our perception of reality itself. The universe is a vast, complex, and beautiful mystery waiting to be explored. As we draw this enlightening journey to a close, let's take a moment to reflect on the monumental role the theory of relativity plays in our understanding of the cosmos. This groundbreaking theory, born from the genius of Albert Einstein, has forever altered our perception of space, time, and reality itself. The theory of relativity is a cornerstone of modern physics, a beacon that guides us through the darkest corners of the universe. It has introduced us to concepts that once seemed unimaginable, like the bending of light, the warping of space, and the dilation of time. These are not mere abstract concepts, but real phenomena that have been confirmed by numerous experiments and observations. Furthermore, the theory of relativity has provided us with a novel understanding of gravity, not as a force, but as a curvature in the fabric of spacetime created by mass and energy. This shift in perspective has allowed us to accurately predict the motion of planets, the bending of starlight, and even the existence of black holes, those mysterious cosmic entities that continue to captivate our curiosity. But perhaps the most remarkable aspect of the theory of relativity is its universality. It applies to all frames of reference, to all observers, everywhere in the universe. It tells us that the laws of physics are the same for everyone, no matter where you are or how fast you're moving. This is a profound and humbling realization that underscores our connection to the cosmos. So, let the theory of relativity inspire you. Let it fuel your curiosity and propel your desire to learn more about the universe. There's a vast cosmos out there, teeming with mysteries and wonders waiting to be discovered. As we delve deeper into the cosmos, Einstein's theory of relativity continues to guide us, shedding light on the mysteries of the universe.
Thank you for watching.